look a little more at electric fields and how to work with them in solving various kinds of electrostatic problems. And then on Thursday, we'll look at how to calculate electric fields for what we call continuous charge distribution. So we're still looking basically at point charges for the moment, but then eventually we'll add these point charges up in order to create a total electric field that is associated with a charge distribution that is uniform, say over a surface or along a line or that kind of thing. And so our main task to begin with is to make sure that we understand what the electric field is and how it differs from the electric force. And so that's something I spent quite a bit of time on last time. I'm going to further try to emphasize that today by first of all looking at the electric field due to two-point charges. And so these are what I call electric field lines. And so these extend out away from the charge and give us an idea as to how strong the electric field is and in what direction it's pointing. But remember that electric fields are vectors and that this is a vector field that has a magnitude and a direction at every point in this space. Okay, so this is just giving us a certain tendency to understand how the electric field works. But to really understand it clearly, what we need to do is look at a certain point. And so what I want to do here is set R equal to 1 meter. And let's have a charge here, Q, that's equal to 10 to the minus 5 coulombs. And then in this case, we'll do the same thing, but we'll change the sign on the charge. We'll make it minus 10 to the minus 5 coulombs. And so I want to look at the electric field at a distance 1 meter away from this charge. So this is where I'm looking to see if I can find out how I can express the electric field in terms of what's been given in the problem. So the electric field, we notice, points straight away from positive. And so that's what these electric field lines are trying to show us here, is that there's a divergence of the electric field lines away from this point. Whereas here, there's a convergence of electric field lines toward negative. And so you could think of this as being a source of electric field, and this is where the electric field goes down the drain. And so for every positive charge in the universe, there's a negative charge in the universe, so that every field line will eventually terminate on a negative somewhere else in the universe. And so this is something that we'll look at in a little more detail when we get to the dipole field later. But for the moment, let's just look at what the magnitude of the electric field is. The magnitude would be 1 meter away. Okay, and so that means in any direction. If I say 1 meter away, it could be 1 meter in this direction, that direction, that direction. So this is my spherical coordinates r hat. And I'm looking then at basically the magnitude of the electric field on a spherical shell that is 1 meter away. And so that means that out here too, it would be coming straight at you like this. We're just taking a cross section of it. But this would be like a spherical shell in which the electric field would emanate in this direction and that direction, and then the cross section of that sphere is going to be a circle. And then similarly on the back side, it would point away. And so if this is the charge then, and this is the radius, K is our Coulomb constant, which we looked at before, 9 times 10 to the 9. So we plug those in. We've done this before. We get 9 times 10 to the 4 newtons per coulomb times r hat. So that means that here it's 9 times 10 to the 4. Here it's 9 times 10 to the 4. Here it's 9 times 10 to the 4. And at an infinity of other points along this spherical shell, it's also 9 times 10 to the 4 newtons per coulomb. And the direction, though, is constantly changing. The direction is going to be to the right here. We take its corresponding point over here, it would be to the left, because it's always pointed away from positive. Similarly, for negative charges, let's do it. We get the same answer. For the magnitude of the electric field, it's still going to be 9 times 10 to the 4, but multiplied by a negative charge. Okay, so the charge here is minus 10 to the minus 5 coulombs. And so at this distance then, r equals 1 meter away. This length here would be 9 times 10 to the 4 newtons per coulomb, but pointed inward toward negative. And there's no force at all. What we're doing here is we're looking at the value of the electric field at each point on that sphere that's a distance 1 meter away. Now, if we want to go 2 meters away, how's that going to change the magnitude of the electric field? Let's say I go out along a straight line. Is it going to be more or less? How much less? By a quarter. Good. So this is going to be at 2 meters away. This will be 9 quarters times 10 to the 4 newtons per coulomb, because you double the distance and it's an inverse square law. And similarly up here, this would be 9 quarters times 10 to the 4. Same deal up here, all the way around. And so the same thing would be true here, that it would be 4 times as small in the direction that points toward the center. So this would be 9 quarters times 10 to the 4. So if we draw a circle around the charge, then we can look for the value of the electric field at some point along that circle. And so basically that's what I did in the last example, where I figured out the electric field last time at the midpoint between a positive and a negative charge. Basically what you're doing then is you're drawing a big circle around each of them. In this case, I think we had 2L was equal to 2 meters, I believe, in that example. So then L here is 1 meter, L here is 1 meter. And so then you have an electric field that points away from positive at this point. That's going to be KQ over R squared, or L squared in this case. I'm calling RL. And then for this one, it's pointed toward negative. So you've got a circle around this one, but that points toward negative. And so that's going to be KQ over L squared. So we got 2 KQ over L squared in our last example that we did last time. Okay, and so that's the way that you construct the electric fields, is you just kind of imagine that there's a spherical shell surrounding this thing, and then you have the electric field vector pointing either straight away from positive or straight toward negative, and the magnitude of it, you just add them together like vectors, and for point charges, that goes like KQ over R squared. I just stated this, but we'll prove that this is true using Gauss's law in chapter 23. Any questions about that? Okay, so once we know what the electric field is, then, and only then, can we put a charge at that location and get the electric force. Once we have a charge, then we can say that force is equal to Q times E, where E is the total electric field at that point. And so that force then is going to be in the same direction as the electric field if this charge is positive. As we see here, force is QE. Force and electric field are both vectors. And so Q determines whether or not it's parallel or anti-parallel. If the Q is positive, then F points in the same direction as E. But if Q is negative, then it points in the opposite direction. Now, sometimes that gets people a little bit confused, so you can go right back to basic principles. If that seems too mathematical or like you have to memorize something, that's not really necessary here, because you can just go back to that simple rule that I started out with: like charges repel, unlike charges attract. Okay, and so if I put a negative charge here, minus Q, then we can use the math. We can say that if the electric field is this way, and that's 2kq over L squared. Remember, this was 2L here. So each one of these is L. So the electric field at this point is 2kq over L squared, but then the force is equal to our charge times E. In this case, it's negative. And so which direction should the force point? If the electric field is this way and this is a negative? To the left. And so we know that because from mathematical analysis, we can see that a negative times E is just going to flip the direction of the force. But again, you don't necessarily want to get too mathematical with these things. Just go back to the basic rule. We know that negative attracts positive and negative repels negative. So that both of those things push it this way. So you don't have to always resort to some mathematical argument that's based on the correct choice of a positive coordinate system. You can just go with the very simple like charges repel and like charges attract.
So if we don't know where the position of that charge is, we would solve for L first, and then we would be able to calculate the charge of it, essentially?
Well, if we didn't know the position of it, we'd need some other constraint, like such that the force is 0 or something else.
Gotcha.
We wouldn't be able to just say, I don't know what the distance is, calculate the force, because then there's too many unknowns.
Right.
Any other questions? Okay, so with that idea in mind, let's just talk for a second about a couple other variations on this. We might have electric field components. So far, we've just been looking at problems where the electric field is in a straight line. But of course, in general, that's not going to be the case. So let's try a problem like this one. Let's say we've got an XY coordinate system like that. We've got a charge here, minus Q, and up here we have a charge plus Q. And let's say these are both at a distance L equals 1 meter away. In this case, 1 meter away from the origin. Okay, so we could think of this as being up along the y-axis, this as being across on the x-axis, but at equal distances away. And so what I see a lot of people wanting to do in a problem like this, when I ask for the electric field at the origin, is they kind of ignore that point and ignore the point that I'm asking for electric field, and they just automatically go to figuring out the forces between these two charges. And so that is, of course, a completely wrong problem to be solving. If I'm asking here for the electric field at the origin, then I'm looking for the disturbance in the space that is produced by these two charges at this location. And I haven't yet specified if there's going to be any charge there or not. And so as long as there's no charge there, there's no force. It's just an electric field until I put a charge there. So what we need to do then is say, okay, well for this negative, I'll just draw a big circle around it. And I know how the electric field lines go. For negative, points toward negative. So that's going to be my E, I call it E1 here. This is charge 1. Let's call this charge 1 and this charge 2. So this will be E2. And then for this one, which way is E1 going to be pointing? Up? in the negative y. Does everybody see that? Because now I'm drawing a circle around this one, and I want the electric field to point straight away from positive. That's going to be my E1. So it's going to point straight away from positive, but my E2 is going to point straight toward negative. So it's really critical that you get this right now, that you understand what it is that I'm doing and why I'm doing it, and not try to memorize this. This requires the understanding of what we were just talking about with drawing those circles, and then always following that rule of having the electric field point away from positive and toward negative. Are there any questions about that before I go further? Yeah.
Do we always act like that charge is positive, the one that we're solving for? Which was
What
why,
charge?
the one with E1 and E2, which is why.
That's not a charge.
Oh.
That is a point in space. That's the whole point of what I've been saying about this is not a force. This is the disturbance in the space that's produced by Q1 and Q2 at this location. Only when you put a charge there, which has not been done, then you get a force. And not until then. So we're just talking about electric fields now.
Okay. Is that space always repelled by positive charges?
It's not repelled by anything. There's no force there.
Okay.
To have a repulsion, you have to have a force. There's no force there. You just have a disturbance in the space here. You haven't put a charge there yet, so there's no force. That's the key to not making that mistake. That's really the whole essence of what is very commonly done, is mix up forces with fields. Okay? And that's not what we're doing here. We're just doing the field itself. That's the whole chapter. Chapter 22 is just the fields, not the forces. We can make it into a force by putting a charge there, but there's no charge there. Okay, so what do we say from the symmetry of this problem about the magnitudes of E1 and E2? They're the same, provided that plus Q and minus Q have the same magnitude. So if I make this 10 to the minus 5 coulombs and call that Q1 and Q2 here is minus 10 to the minus 5 coulombs. Then we have the magnitudes of the mean equal, and so therefore the magnitude of E1 equals the magnitude of E2, so that we can just set Q1 equal to Q2 equal to big Q. So then this will just be K big Q over R squared. And so that'll be 9 times 10 to the 9 Newton meters squared per coulomb squared times 10 to the minus 5 coulombs divided by 1 meter squared. So we're getting the same number just because I'm using easy numbers to evaluate, but there's nothing special about 9 times 10 to the 4 newtons per coulomb. Or eventually we'll see that that also has units of volts per meter. That's what we did in lab when we figured out the length of the spark and then figured out the voltage. So when we get to volts later, we'll also write the electric field in those units, which are equivalent to newtons per coulomb. So what I've got here then is a 9 times 10 to the 4 Newton per coulomb, and here I've got a 9 times 10 to the 4 Newton per coulomb. So those are my two vectors, E1 and E2. And so if I want to write E total, I can write it in Cartesian coordinates as 9 times 10 to the 4 newtons per coulomb I hat minus 9 times 10 to the 4 Newton per coulomb times J hat. Okay, so this is my J hat component. That's negative because it's pointing straight away from positive, and the I hat is pointing in the positive direction straight toward negative. And so that gives me the electric field in Cartesian coordinates. If I want it in polar coordinates, I can see what's going to happen here is that when these two add, you're going to get an E total that's equal to the square root of 2 times E, where the value of E here is what I was calling E1 and E2. Okay, So that's the hypotenuse of this right triangle. If these weren't equal in length, then you would have to do the Pythagorean theorem that because this is a 45, 45, 90 right triangle, I can just write this as the square root of 2 times e. And so that would be square root of 2 times 9 times 10 to the 4 newtons per coulomb. 1.414 times 9 is 12.7 times 10 to the 4, or 1.27 times 10 to the 5 newtons per coulomb. So that's the magnitude of E total. The direction would be 45 degrees from the x-axis or 45 degrees from the y-axis. And so we could say for the direction, just 45 degrees below the horizontal. And so that then is essentially just putting this in terms of r and theta, because theta is the inverse tan of the opposite side, E1 over E2. But that's just the inverse tangent of 1, which is 45 degrees, or pi over 4 radians. And so that's just the difference then between putting my final result for the electric field in terms of Cartesian coordinates or polar coordinates, which is essentially the same thing that we did all of last semester, but it was just with other kinds of forces in 288. Any questions about this? Okay, now once we have that, if we wanted to, we could put a charge there, just like I did in the last example toward the end of class last time. And then we could get the force on that charge. But what I want to do next is take a look at a problem where we have a constant electric field.